Hi, in this screencast, I'm going to talk to you about LOL diagrams, which is a useful way of analyzing the energy in systems. Let's get going. Okay, so remember, if a system is closed, what that means is the mechanical energy of the system is conserved. It tells us that the only forces acting are conservative forces acting between objects that are in the system. Okay, and for example, let's just say I have a person releases a clay ball from a height at which has 100 joules of gravitational potential energy. I want to draw an LOL diagram for the object Earth system, with the initial state being when it's at rest in a person's hand and the final state being right before it hits the ground. Now, I got to be careful and pay close attention to what's considered to be my system. If my system is the object and the Earth, in that case, I can have gravitational potential energy. But if I was told that the Earth isn't part of the system, then the Earth is an external force doing work on the system. So I got to be careful about that. Now, so let's just see how I draw an LOL diagram. So LOL comes from the way this looks, LOL, but really what this is I have two histograms and a circle in the middle. Now, the first histogram is the initial state of the system in terms of its energy. So I have three spaces for the mechanical energy that has: kinetic, gravitational potential, spring potential. And I'm going to draw histograms here to show how much energy it takes in each form. The circle is where I'm going to write which objects are in the system, and if there's an external agent acting on the system, I'm going to put it outside the circle if it's not part of the system. It's outside the system. And then over here I have the final state. Again, I have K, U, G, and US, but I also have this one here, delta E, sometimes delta E thermal. Can write it either way. Let's talk about what that one means. Okay, so this refers to thermal energy, or what we also call internal energy, and basically it's the energy of random atomic motion. So if I have a collision that happens, some of the mechanical energy is going to be converted into the random kinetic energy of the atoms. And so that means it reduces the overall kinetic energy of the system, at least in terms of mechanical kinetic energy. And now I have this random atomic kinetic energy, which is not considered mechanical energy because you cannot convert it back into linear kinetic energy. So the big idea here is thermal energy, although it's in our system, is non-mechanical energy. And so if I evolve any of that, the system must be open. So anytime you have anything in this column, it is an open system. Let's go back to the first thing we had here. We said the person drops the ball, has 100 joules of gravitational potential energy. So I'm going to draw a histogram showing in the column for UG 100 joules. Now, it's a good idea to do it as little boxes, and each box represents a certain amount of energy. So I just use, instead of 10, I didn't want to have to draw 10 of these things. I just chose 20 joules per box, so I need 5 boxes. It's up to you what you want to do here. You can even not do boxes and just write how many here. It's up to you. But the boxes are a good idea to make you think about conservation of energy. Now here, I'm going to write what's in my system. My system consists of the Earth and the clay ball. And now my final state is right before it hits the ground. So all that energy would be converted into kinetic. And I see that there's nothing here, and that I have 100 joules here, 100 joules here. That tells me it's a closed system. No energy came into or out of the system, and no thermal energy was evolved. Now, what if I was told the Earth was not part of the system? And you've got to be careful because College Board will tell you this. Now, in that case, the Earth doesn't go inside the circle here. The Earth is an external agent doing work on the system. So I'm going to put Earth out here rather, and it's still going to cause the object to end up with 100 joules of kinetic energy. There's no getting around that. And just choosing a different system doesn't change the outcome. However, I'm going to show the Earth adding 100 joules into my system. Now this is just a little arrow indicating that this 100 joules is going into the system here, and it's coming from the Earth. Since energy is being added to the system, that means there's external work being done on the system. It is an open system. The mechanical energy of the system increased, so it's clearly an open system. Hey, what's that? I did, yes. Okay, sorry about that. So let's look at another one. Okay, let's go back and say, in this case, we have the Earth is part of the system, but we're told to draw an LOL when the final state is after the ball has hit the ground and come to rest. So once again, since the Earth and the clay ball are both part of my system, then I have 100 joules here. But afterwards, I don't have 100 joules of kinetic energy here. Instead, I have 100 joules of thermal energy. So it might look like, oh, well, I have the same energy on both sides. It must be a closed system. But actually, it's an open system because thermal energy is non-mechanical, so therefore it is an open system. Now let's try this one here. Let's just say a person drops the clay ball. Instead of just letting it go, the person pushes it down. They apply 80 newtons of force across 0.5 meters of distance. And so I'm going to draw this LOL to see what we've got here. So the person had the clay ball, initially had the 100 joules of UG like it had before. My system consists of the earth and the clay ball. But this time, the person pushed 80 newtons across 0.5 meters, so that means they did 40 joules worth of work. So I'm going to draw the person, which is not part of the system, outside the circle, and I'm going to show them adding 40 joules of energy in the form of the work they did with the positive work they did with their hand moving in the direction of motion, going into the system. And so that means if I have 100 here and 40 here, I have to have 140 over here. Okay, and since there's 20 joules per box, that means I need a total of 7 boxes. So let's see what I have. Now, first of all, we're told here, I should have pointed this out, that we want to draw it when the ball is halfway to the ground. Now, that's an important thing to pay attention to. It says draw it when it's halfway to the ground. So if I have 100 joules initially, halfway to the ground, it has 50. Each box is 20, so I'm going to go 20, 40, and this time I'm going to represent 10. I'm just going to draw half a box, so that's 50. So what I see here is I have 50 here, there's 50 here. That's the 100 I started with, and here's the extra 40 that I put in there. It's going to have more kinetic energy than it would have otherwise. Now, the system is considered open for 2 reasons. One, the mechanical energy increased, or changed at least, and also that there was external work done on the system. Now here, I'm going to do the same thing, but in this time, the clay ball is going to be dropped, but when it's halfway to the ground, the person is going to apply an upward force and do 40 joules worth of negative work to it. All right, let's see what this would look like. So I'm going to start off with, I have 100 joules of gravitational potential energy, and I have a person who's outside my system. In my system, I'm going to put earth and clay ball. But this time, the person is doing 40 joules of negative work. So I'm going to show that the arrow on those 40 joules going out of the system and into the person. So this shows me that 40 joules has left the system. So I need to have 40 joules less energy here than I had in my initial system. So again, I'm halfway to the ground, which means I have a total of 50, 20, 40, 50. But the total on this side has to be 60 because I have 100 minus 40. So that means I only have 10 joules of kinetic. And that means, therefore, my system is open because external work was done on the system and the mechanical energy of the system has changed. Now let's try this one here. I have 2 objects in space that are going to collide and stick together. They both have 30 joules of kinetic energy initially, and after they hit, they come to rest. They stop each other. Okay? We'll study this when we do momentum later in the year. So what I'm going to do is I'm going to add up the total kinetic energy of the system beforehand. Since I'm in space, I'm not going to have any potential energy in this case. So that's 60 joules. So I'm going to use 10 joules per box here. So 1, 2, 3, 4, 5. That's 60 joules. Here are my 2 objects that make up the system. Afterwards, there's no kinetic energy, there's no potential, there's no spring energy. So I just have 60 joules of thermal energy. That makes it an open system because that's not mechanical energy. The mechanical energy of the system went down. Even though the force was internal to the 2 objects involved, it was a non-conservative force. It was a normal force. And the only conservative forces are gravitation and spring. And that's why I didn't keep my mechanical energy. Instead, I converted it into thermal energy, making the system open. Well, now I have a box sliding up a rough frictional surface, and I see from the diagram that it starts off with 120 joules of kinetic energy, and at the top it has 20 joules of gravitational potential energy and 20 joules of kinetic energy. And from this I can determine how much thermal energy must have been involved. So I'm going to start off and say I have 120 joules. I don't want to draw 12 boxes, so I'm going to draw 6 boxes each, meaning I have 20 joules per box. My system consists of the earth in the box. And so afterwards, in my final state, I have 20 joules of kinetic, I have 20 joules of potential. Now, I have to account for all 120, and so that means I have to have 80 joules here of thermal energy. The system is definitely open in this case because my mechanical energy went down and a non-conservative force acted on my system, that being friction. Okay, so now here's a tricky one. Don't get caught with this one here. In this case, I'm going to push a box. A person is going to push a box up an incline. They're going to apply 60 newtons of force and push it 10 meters. Now look at this. It starts off, it has 400 joules of kinetic and 100 joules of gravitational. Afterwards, it has 100 joules of kinetic and 400 joules. Now look, that mechanical energy and that mechanical energy is the same. Don't be fooled. Let's see what happens here. You have to keep in mind the person did 600 joules worth of work on the system, positive work. They pushed the object in the direction it was going. So I have to show 600 joules going into the system from the person. Now, I started off, I had 400 kinetic and 100 gravitational. Afterwards, I have 100 kinetic and 400 gravitational. The mechanical energy is the same, but I must have this extra thermal energy here because I added energy to the system. This is definitely an open system. Hey, thanks for watching this. You'll get used to it. It's not that hard. Thanks for watching. We'll see you in class.